Welcome to this explainer. I'm absolutely thrilled you're tuning in today. We are going to take the seemingly complex world of chemistry and transform it into a highly relatable, genuinely fascinating recipe book of the universe. We're talking about the invisible magic that makes our physical world tick. So let's just dive right into this. I want you to picture two completely different things: a rusting iron nail left out in the rain and the lunch you're digesting right now. What could those two things possibly have in common? I mean, on the surface, absolutely nothing, right? But at a microscopic level, they're united by a shared fundamental process. They are both profound chemical transformations happening right in front of us.
Here's our quick roadmap for today. First, we'll look at spotting a chemical change. Then, the language of chemistry. Third, we'll break down 5 types of reactions. And we'll wrap up with chemistry in everyday life.
All right, let's kick things off with Section 1, Spotting a Chemical Change.
Before we get into the really complicated reactions, we kind of need to establish the ground rules, the difference between what stays the same and what permanently transforms. Think about a physical change for a second. If you melt an ice cube or tear a piece of paper, you haven't actually created a new substance. You can always freeze that water right back into ice. It's temporary. But contrast that with a chemical change. When iron rusts, or say you burn a strip of magnesium ribbon, you're creating entirely new substances with entirely different properties. A physical change is really just a temporary disguise, while a chemical change, that's a permanent transformation. So, how do we actually know this everyday alchemy has happened? Well, we basically look for a visual checklist of clues. You might see a change in state, like solid wax burning away into a gas. You might notice a change in color, like gray iron turning into that reddish-brown rust we all know. You might see the evolution of a gas. Think bubbles of hydrogen popping up when zinc meets sulfuric acid. You might even feel a change in temperature. That could be an exothermic reaction throwing off heat, or an endothermic one absorbing it. Or amazingly, you might see the sudden formation of a precipitate, which is basically a solid that just magically emerges from a liquid mixture.
Moving right along to Section 2, the language of chemistry.
Now that we know the visual signs, we need a way to translate and actually write down these incredible transformations. Think of every chemical reaction as having a starting line and a finish line. We call our starting materials the reactants. These are the substances actively taking part in the reaction, and we always write them on the left-hand side. The finish line brings us the products. These are the entirely new substances formed, and they sit over on the right-hand side. It's pretty simple. We're just tracking what we start with and what magical new thing we end up with. Now, scientists could definitely write everything out in long, drawn-out sentences. But why do that when you can use a cheat code? We use chemical symbols to create a really concise, universal recipe. Sure, writing magnesium plus oxygen becomes magnesium oxide totally works. But writing Mg plus O2 becomes MgO, that's way faster, it's universally understood, and honestly, it lets us see the actual atomic building blocks at play. But there's a bit of a catch here. Thanks to the law of conservation of mass, you can't just create or destroy matter. It's literally impossible. That means we have to do some strict atomic accounting. The number of atoms on the reactant, left side, has to perfectly match the product, right side. We do this using what's called the hit and trial method. Take the rusting of iron. Fe plus H2O yields Fe3O4 plus H2. First step, you count the atoms on both sides. Then you start multiplying the molecules to fix the biggest imbalances. Usually you start with oxygen, then move to hydrogen, and finally tackle iron. You just tweak those multipliers until the left and right sides are perfect atomic mirrors of each other. It's like a giant puzzle. To make these recipes even better, we add a little extra flavor. We use these tiny letters and arrows as extra cheat codes to tell us exactly what the substance looks like and behaves like out in the real world. A little S means solid, L is for liquid, G is gas, and AQ means aqueous, basically dissolved in water. If you see an upward arrow, that means a gas is floating away. And a downward arrow, that tells us a heavy solid precipitate just fell right to the bottom of the beaker. Which brings us to Section 3, 5 types of reactions. So, now that we're pros at writing the recipes, let's categorize the beautiful chaos of these reactions. Virtually every chemical reaction follows one of 5 fundamental patterns. Think of these as our master legend: combination, decomposition, displacement, double displacement, and redox. Let's run through these and see how they build our entire understanding of the chemical world. First up, we've got the combination reaction. The formula is super simple. A plus B becomes AB. Two things literally combine into one.
A fantastic real-world example of this is the slaking of lime. When you vigorously mix solid quicklime, that's calcium oxide, with water, they combine to form calcium hydroxide, or slicked lime. It's a highly exothermic reaction, which means it aggressively releases a massive amount of heat. Fun fact, this exact mixture is traditionally used to whitewash the walls of buildings. On the flip side, we have decomposition, which is exactly what it sounds like, the total opposite. One reactant breaks apart into two or more simpler products. But here's the thing. To break those chemical bonds, you have to force them apart using energy. We can use heat, like when we thermally decompose lead nitrate. We can use electricity to literally split water into hydrogen and oxygen gas. Or, and this is wonderfully cool, we can use light for photolytic decomposition. It is utterly fascinating that we can harness sunlight to break down silver bromide. In fact, that light-driven chemical reaction is the very foundation of old-school black and white photography.
Next on the list is the displacement reaction. I like to think of this one as a chemical power struggle. A more reactive element will quite literally boot a less reactive element right out of its compound. Imagine dipping a regular iron nail into a bright blue copper sulfate solution. Because iron is more reactive, it displaces the copper. The solution chemically changes right before your eyes, fading from blue to light green, while a brown coating of defeated copper settles right onto that iron nail. Then we have double displacement. Think of this one like two compounds mutually swapping dance partners mid-song. When you mix a sodium sulfate solution with a barium chloride solution, they exchange ions almost immediately. The newly formed barium sulfate is completely insoluble, so it instantly forms a brand new, solid white precipitate that just falls right out of the liquid. Our final category requires just a slight shift in perspective: oxidation and reduction. These two are perfect, inverse mirror images of one another. Oxidation is what happens when a substance gains oxygen or loses hydrogen. Reduction is the exact opposite, the loss of oxygen or the gain of hydrogen. And when these two mirror image processes happen at the exact same time in the same equation, boom, we get a redox reaction, reduction and oxidation. Let's look at the reaction between copper oxide and hydrogen. The copper oxide loses its oxygen atom, meaning it gets reduced. The hydrogen gas happily picks up that very same oxygen atom to become water, meaning it gets oxidized. It's this beautiful, synchronized transfer of oxygen from one agent to the other.
Okay, so we've decoded the equations, we've balanced the atoms, and we've mapped out the archetypes. But let's pivot for a second and ask the most important question. Why does understanding these microscopic forces actually matter to you, right now in your daily life?
Let's dig into that in Section 4, Chemistry in Everyday Life. Let's bring it all home by looking at the darker, honestly more destructive side of these reactions and how we can use our newfound knowledge to control them. The most obvious one is corrosion. Corrosion is really just an everyday, slow-moving oxidation reaction that relentlessly eats away at our metals. It's the flaky rust destroying an old iron bridge. It's that black coating tarnishing your silver jewelry, which is caused by hydrogen sulfide in the air. It's the iconic green copper carbonate coating on the Statue of Liberty. But here is why learning this matters. By understanding the chemical equation behind corrosion, we gain the power to stop it. We protect our metals by throwing up physical barriers to stop the oxygen. We use techniques like painting, oiling, or galvanization, which cleverly coats the metal in a protective layer of zinc. And unfortunately, it's not just metals. Oxidation attacks our food too. You know that foul smell of old frying oil or the terrible taste of a stale snack? That's rancidity. It's literally the oxidation of fats and oils. But once again, chemistry provides the solution, and we combat this reaction every single day. Have you ever noticed that when you open a puffy bag of potato chips, there's a lot of air in there? Well, that air isn't regular oxygen. We purposefully flush the packaging with inert nitrogen gas to completely block the oxidation process. We use refrigerators to slow the reaction down with cold temperatures, and we even add chemical antioxidants like BHA to our foods to fight the oxygen off before it does damage. We've explored how a really simple, elegant set of atomic rules governs absolutely everything, from the rusting of a massive iron ship to the preservation of your favorite snacks, all the way to the very digestion keeping you alive right now. It truly is an everyday alchemy. So it kind of leaves us to wonder, the next time you walk down the street or cook a meal or even just take a breath, what other hidden chemical recipes are waiting to be decoded right in front of your eyes? Thank you so much for joining me in this explainer, and definitely keep looking for the magic hidden in the mundane.